So we'll do the toboggan problem here that we did in class, or at least introduced in class. And what we have is somebody that starts up here, two people on a toboggan at A. They end up down at the bottom of a hill, which would be 3 meters. And so really this allows us to do a nice state 1. Down here at the bottom, we can do a nice state 2. And so up here, depending on where you put your datum, define Vg equals 0, put our datum for potential up here, we would end up with Vg1 equals 0, kinetic energy 1 also equals 0, U1 to 2 non-conservative equals 0, no friction, neglecting friction. And then we end up at the bottom, Vg2 would be minus mg times 3 meters. And what we have at the bottom is all kinetic energy, 1/2 m v squared. So that would be the velocity of the toboggan down at the bottom of the hill. So if you go ahead and do that, you'll find that the velocity of the toboggan is equal to 7.67 meters per second. And again, understanding up here, right, the mass is going to be all three things together. So we'd end up with 10 plus 40 plus 45 would be what we'd be using for the mass. Obviously the mass will cancel out there, but we'll end up using it in just a moment. And now we end up with somebody getting pushed off. And so what we have is an internal force which causes that separation. Right? Generally things are either going to collide together, which they would join. So we have a collision, or a separation would just be the exact opposite of that. So what we're going to end up doing is analyzing across the push, and let's see what the velocity is. We're asked to define that we want the velocity of the toboggan after this push off occurs. So right here we've got two people on the toboggan, and so right here we've got the mass total times 7.67, right, which we found from work energy above. We've now got somebody who just got pushed off, and so that was done by an equal and opposite force. We've got normal forces, we've got weights. Again, those are all by delta t, by delta t, by delta t. This in here is F times delta t. And so at the end we have a single rider on there, and we've got somebody again flying with a different velocity at the moment. So at this point now, the mass of this 3-particle system, two people, there's no longer together. So here the mass is going to be 10 plus 40 times the velocity of the toboggan. Up here we've got 45, which is the mass of the boy, times the velocity of the boy as he jumps off, or is pushed off, is pushed off. So we need our coordinate system. And so we end up here with a desire to some linear momentum in the x direction. But as we do that, we're going to end up finding that 10, 40, 45 times the 7.67. Again, that would be negative. It's going to the left. I've defined to the right positive. I've got 0 from my middle term. And then I've got a minus 50 times VT, and then minus 45 times the velocity of the boy. So fortunately we end up with one equation and two unknowns. So the unknowns here are going to be the velocity of the toboggan and the velocity of the boy. And so we're just going to scam right back up to the problem statement. And as we re-look at that, we see that we're told something about a relative velocity. So we're going to end up using kinematics to give us another equation here. So I would know that the velocity of the boy, again in vector form, is the velocity of the toboggan plus the velocity of the boy relative to the toboggan. And again, we need to use our convention. So up here, when I'm talking about the velocity of the toboggan, the velocity of the boy, those are all going in the negative x direction as I defined it. So we would end up with minus VB in the I direction is equal to minus VT in the I direction. And then we're told that we have a relative velocity of 2. So from this, I've got that the velocity of the boy is equal to the velocity of the toboggan minus 2. So that is simply all I'm going to do is just take that answer right there, and I'm going to put it right in that equation right there. And so when I solve that, I'm going to end up finding out that the velocity of the toboggan was equal to 8.62 meters per second. And I would say, or 8.62 meters per second to the left, because a positive number here, something that's positive, ends up saying that we have drawn it in the correct direction on our impulse momentum diagram. And so you may actually wonder, well, what if I had drawn the velocity of the boy in the other direction? So what I'm going to do with you is just kind of filter that through here. So I'm going to erase this. I'm going to erase his velocity vector right there. And so what I'm going to do now is say that I, let's say, drew it in that direction because I wasn't sure what direction it was, his velocity is going. So how does this thing filter through here? So as we move down to this next equation, we end up with a positive right there. I'll kind of highlight that. That now it's turned into a positive. And now what we also see is we're going to have a slight variation in our relative velocity equation. So the velocity of the boy now drawn in the picture would be positive. Nothing else has changed. So that now tells me that the velocity of the boy would be represented now by the equation of minus VT plus 2. And so if I go ahead and plug that right back in there, the math will work out such that we end up with exactly the same answer right there. And so, however, what we also find is that once we take and use that value, we would find that the velocity of the boy is equal to minus 8.62 plus 2, or minus 6.62, or 6.62 to the left, because now our picture up here has that arrow drawn to the right, and so the negative would mean that it's actually going to the left, which is what we would have found which is what we found when we had the arrow drawn the other way. All right, our last problem would involve somebody that's jumping off one cart and onto another. And so this boy is both going to separate here, right, and then they're going to join, or we're going to have a collision on this side. Both, again, separation and collision would be an impact force. And so as we read the problem statement, we would just kind of dig out here that the velocity of the boy relative to car A is equal to 4. And so I'm going to do a little bit of work on this. The velocity of the boy is equal to the velocity of cart A plus the velocity of boy with respect to A. I know that the velocity of the cart is 0. So what we would find is that the velocity of the boy has to be equal to the relative velocity. So we'll end up using that a little bit later here. So what we're going to do again is starting with the separation part. So we'll do an impulse momentum diagram to get across the separation. So here we've got He's actually on, has not quite jumped off yet. We're going to have a separation, and then we've got after velocities of both pieces. So before, we've got 0 here. We've got 0 velocity. This thing is at rest. All right, what are our impact forces, right? Anything, I've got the weight of the cart, I've got my normal forces, I've got the weight of the boy. And again, I'm going to take these together. So I end up with F delta T. Obviously, these are all delta T as well. So there's my impulse force. And taken separately, then I've got, and again, I don't know what direction the velocity of cart A is going. I can just draw it in any direction. I do know that the boy is going to be going to the left as he jumps, so we'd end up with the mass of the boy times the velocity of the boy, and that would obviously have some geometry with it, 5 to 12. So I'm just going to fill in just a little bit more. There's N, there's our normal forces times delta T. And so we've got a lot of arrows in the vertical direction right here. And so what we're going to end up doing is avoiding all those arrows by summing linear momentum in the X direction. And so when I do that, I end up with nothing in the first diagram, nothing in the second diagram. And that would then end up with minus MA, velocity A, minus MB times, and I'm going to use just the component, obviously, in the X direction. So we end up with a ratio of masses, and so we'd end up with the velocity of A is minus 3/4 the velocity of the boy in the X direction. And so what I'm going to do now is apply the relative velocity equation. And I'm going to apply this only in the X direction. All right, so just to remember the velocity of the boy in the X direction, right? This is a vector equation. It's going to be the velocity of A in the X direction plus the relative velocity of the boy with respect to A. So we have to go back to our picture as to how it's drawn. So we'd have, right, the velocity of the boy is going in the minus X direction. So we'd end up with minus V boy X is equal to, we've drawn A in the negative direction, and the velocity relative, we're showing from up here in the picture, right, is also going to the left. So we'd end up with minus just a fraction of it, V boy with respect to A. And so we now have an equation, and we're going to plug in right here, take our answer that we got for the velocity of A. That goes in right there. And so then we are able to solve for the velocity of the boy in the X direction, and numerically it comes out to be plus 2.11 feet per second, and positive would mean it is 2.11 to the left, because that's how we have it drawn up here in our impulse momentum diagram. So we can also find the velocity of A would be minus 1.58, or 1.58 to the right, which we would think if one had a velocity going left, that one would have to be going to the right. All right, so now let's look at the joining of the two new carts. So I end up with the boy right in the air there just before we actually have a collision, and afterwards they are going to be sitting connected together. So let's go ahead and throw our coordinate system on there. And so what do we have? We have a cart at rest. We have a boy coming in with some velocity. And he's going to have two components of velocity. It's going to be the mass of the boy times v boy in the x direction, which we just found, of 2.11. And that would obviously be the mass of the boy times the velocity of the boy in the y direction. All right, we've got our big impact forces. We've got all of our weights times delta t. We've got normal forces times delta t. A little messy in here. And in the end, we're going to have both of these entities together. So we would have mass of the boy plus the mass of cart B times some v final, some velocity after the impact. So again, the way we're able to avoid all those y direction forces in the integral of f dt is we're going to sum linear momentum in the x direction. And when we do that, in the first diagram, we've got a cart at rest and a boy with a negative times v boy x. And I'll replace that again. I already know what that is. That's going to be 2.11 that we're going to use there. That's going to equal, now I've got 0, I should go plus 0, and then that's going to equal minus the sum of the masses, so the mass of the boy plus the mass of B times V final. All right, and again, it's negative because I've drawn the arrow opposite what I've used sign convention for. And so I now have one equation, one unknown, so I would have the fact that V final is equal to the mass of the boy times 2.11 divided by mass of the boy plus mass of cart B. And so the final velocity would be 0.94 feet per second. It's positive, which means I would say 0.94 feet per second to the left.